Hi viewers, this is Dr. Gunamani Jena, and in this video we will be presenting about this self-organizing map of artificial neural network. This self-organizing map what we are going to discuss, this is so important because of 2 or 3 reasons. First one, the self-organizing map, it is a clustering algorithm and it was developed in 1972. It creates a map of relationships among the input pattern, and you will be happy to know that these are purely unsupervised type of learning. And you know clearly about this unsupervised learning, we do not know the output or the input for the particular input, what is the output, that we do not know. It's clear? So in this case what it try to do, it creates a map of relationship among the input pattern, and the self-organizing map output nodes, it corresponding to unknown clusters that the SOM finds in the data autonomously. That is the thing it does here. So as I told you that this SOM follows unsupervised learning, and it explains the neurobiological phenomenon and is similar to how a newborn baby learns, as he has no idea what is right or wrong. So the self-organizing map has the ability of a network to learn and organizing the information without knowing the correct answer to the input pattern. So it does not know the correct answer for that one. How a newborn baby learns all things, it is similar to that one. Then if you come to the details of this thing, this SOM model, it is used for dealing with problems with complicated algorithm, and especially in robotics where the input is inaccurate and accompanied with noise because of sensor reading, it proves more effective. Is it clear? So especially we are using for this robotics where the input is inaccurate, it is not accurate, and also there are some noises because maybe the sensor reading or the whatever the cameras we are using, all things are there. It is also capable of dealing with problems which are prone to unexpected changes and lack of proper mathematical foundations. Those cases also it is suitable. Then in this self-organizing map, the first of all we will be going for this coherent self-organizing map. This coherent self-organizing map, it has a single layer of node in addition to the input layer. That means input layer is one layer. In addition to this input layer, it has one more layer. And as you know that the input to the nodes of the layer, it is either propagated from the environment, that is means outside the nodes of the layer, or from the nodes. That means if first one is the node, the layer of nodes, if it is outside those nodes, that means input is not taken from this node, then we call it from the environment. If the input is taken from the nodes within the layer, so this is the second option. So first of all, we initialize the weight vectors of the nodes. Then both weight vector and input vectors are normalized to a constant. So why you go for this normalizations? If the vectors are not normalized to a fixed length, then the algorithm is modified, right? Then the coherent net, it aims at using the coherent learning to adjust the weight and finally result in pattern classifications. As I told you that in case of supervised learning we don't have any problem, but in case of unsupervised type of learning we go for this classification. That means the input you classify into some of the class or group, and here the out j, which is equal to a function of x into wj. As you know, x is the input vector and wj is the weight vector of unit j, and here the net may respond to several output categories on the training, but only one of the neuron has to respond. So additional structures are added in the network to force the network to make a decision to which one unit will respond, right? And the mechanism by which only one unit is chosen to respond, we call it as the computations. The mostly used computations among the group of neurons is winner take all. That means only the winner neuron will have a non-zero output, and all the remaining will be suppressed and they will have 0, right? Then what is the architecture of this Cohen network? For functionality of the Cohen self-organizing map, we must have clear idea about the clustering, the learning of this network, and statistical model. Three things are important. So first of all, we are going for this clustering, and you have idea about this clustering. Here clustering means grouping the input pattern according to their similarity. Say suppose some cows are there, small or big, all the cows will be clustered one. So it is done by competing learning, and a number of nodes or neurons are competing with each other. The node which generates the output first is the winner, obviously. In a competition, suppose a running competition, who reaches the destination first is the winner. And node with the largest activation, only they are the winner. Okay, that means, are you following me? So these nodes and its neighbors are allowed to learn from this current input pattern, and all other nodes are suppressed to the 0 activation level. So this is the principle or the architecture of this Cohen network. And then you go for this concept of learning. Here learning is purely weight adjustment. The weight adjustment for this winning neuron and neighbors are done as follows. So the new weight W new, which is equal to old weight W old plus nita into x minus W old. So nita is the learning rate coefficient, you know, and x is the input, and so x minus W old, what is that? You multiply the nita, that is added to the old weight, so it becomes the new weight. So this is the learning. Then the third one is the statistical model. Here input vectors are selected randomly according to the probability density function of the input data set, right? And the probability of input vector being closest to the weight vector, it is 1 by n, where n is the number of Cohen neurons. So it is based on the n, it is decided. Now we go for the normalizations. As we discussed about the normalizations, both the input and weight vectors are normalized before they are applied to a network. Normalization is done by dividing each component of an input vector by the square root of the sum of the squares of all the vectors. For example, suppose x1, x2 up to xn are the input vectors. So x1 square plus x2 square plus up to xn square. So their square root, okay, you get that one, that you keep it in the denominator. In the numerator, suppose I am finding for this x1 dash, so x1 dash is equal to x1 divided by this denominator. Similarly for x2, so this is x1 dash means the normalizations of x1, right? So like this we go for the normalizations. Then we go for the Cohen network. So it has two layers, as I told you, that one the input layer and the other is the output layer, or we call it the Cohen layer. Then how the training takes place? We have studied that only one neuron activate for a given input vector. Prior to training, the weight vector is normalized to make a unit length. Okay. Now the network is trained according to the following algorithm. First one, apply input vector x sequentially, one by one. We calculate x minus wij, xi the input and wi the weight. We calculate these things and compute the square root of the summation of the squares. That means xi minus wij, their square and their summation, and finally we find the square root, that we calculate as d. So d is the distance between xi and wij. And neuron with minimum distance is the winning neuron, because who reaches first, that is the winning. Now we can train the group of neurons closest to the winning neuron. That means the winning neuron and its neighbor, they are only trained. How do we train? We train by the weight adjustment. How to go for the weight adjustment? So wjn minus 1, that is the new weight, which is equal to wjn old weight minus alpha into x minus wj. So it is the principle. Based on this we go for the training. Okay, alpha is the learning rate coefficient here. So based on this we can go for that one. Then this is about the Cohen layer, and another layer we called as the Grossberg layer. It was developed in 1988. Here what we do, the output of the Cohen layer, what we discussed previously, it is provided as input to the Grossberg layer. That means the net j here, which is equal to net I, previous net input into wij. Are you following me? At ith level the net output is net, at jth level net output j. So what is the output at net? That becomes the input for the net j. Are you following me? What is the output for net I? That becomes the input for net j. Okay, jth layer. So then we calculate the net j. Here net j is the net output of Grossberg neuron j, and net I the output of Cohen layer. As I told you that wi is the corresponding weight, because in between two nodes a weight is to be applied, that is wij. Now how do you go for the training of the Grossberg layer? As you know, the training is only the weight adjustment. So wij n plus 1, that is the new weight, is equal to wij n, that is the old weight, plus beta into y minus wij into n into out j. Okay, here beta is the learning rate coefficient I told you, y is the output, and wi is the weight, and out j is the output which is already processed by the some function, right? And beta it is taken 0.1, and y is the defined output, right? And the Grossberg layer will coverage or will converge to the average value of the desired output, and the weights of this Cohen layer are trained to the average value of the input, and the Grossberg training is a supervised. You remember that Cohen is unsupervised, but the Grossberg is the supervised type. So method used for determination of this neuron. First method use dot product of input vector and the weight. So input vector and the weight, that dot product, that means that sum of the product of this input and weight, right? That. So it gives the net input to the corresponding cluster unit, and the largest dot product corresponding to the smallest angle between the input and the weight vector is there of unit length. Then in the second method, it uses the Euclidean distance between input vector and the weight vectors, that what we calculated x minus wij or xi minus wij. It uses the unit whose unit vector has the smallest Euclidean distance from the input vectors. Okay, so this is the thing done. And architecture of this Cohen self-organizing map. This architecture is similar to the competitive net architecture. Here the training takes place over an extended region on this network centered on the maximally active mode, right? And it uses the concept of the neighborhood. The neighborhood may be fixed by the spatial relationship between the nodes with self-organizing layer, and the neighborhood are shown at 1, 2, 3 and at a unit distance from the node, and winning units are indicated by hash, remaining are indicated by star. So this is given here, you can check it here. You got it. All the things what are there, you can see these are all the star, this is the hash, this is the one, all things it is given. If you go back to the previous one, he is telling winning is the hash. What is the winning? Winning at the center, it is as hash, right? You get it now? Can you see here the winning at the center? This is the thing. So get. Then what you get? Then the neighborhood are shown as 1, 2, 3, 4. Where is 1, 2, 3, 4? So this is 1. This is 1. Here these are for this winning. These are the immediate neighbors, and 2. This is another neighbors. So these are the distance neighbors, right? Okay, 1, 2, 3. These are the unit distance from the node, and also the remaining are indicated by the star sign. Remaining are indicated by the star sign. See, all other things are indicated by the star sign. You got it now? So this is the principle. Then what are the application of the self-organizing map network? See, the self-organizing map, what I told you, that is a unsupervised type of learning, and in the real-time applications we usually come across with this unsupervised type of learning. Oh, when you go for the speech recognition has 3 parts. First, we sample the speech signals and extract the data. Second, word processor used to find the probability of these words in the vocabulary that matches the features of the spoken words. Third, the sentence processor, it determines if the recognized word makes any sense, that is the semantic meaning in the sentences. It also removes the noise inherent with the speech. And also the second is the robot motor control, it is also done here. So these are some of the application of the self-organizing map. I hope you have understood the basic concept of the self-organizing map, the Cohen self-organizing map, and also the Grossberg Cohen map. Okay, so if you like this video, If you then you can share with your friends, and also don't forget to subscribe also. And if you give some comments, based on that I will be going for the next video on this radial basis function neural network, the perceptron, and also support vector machine. Thank you for watching this video. Thank you. Take care of yourself. Goodbye.